Today is 28th March. It's 7:42 a.m. and I'm continuing the reading from Using SQLite by J.A. Krebich. And today's chapter that I'm going to read is the select command, chapter 5. The select command is used to extract data from the database. Anytime you want to query or return data stored in a database table, you will need to use the select command. In terms of both syntax and functionality, select is the most complex SQL command. In most applications, it is also one of the most frequently used commands. If you want to get the most out of your database and your database designs, you will need a solid understanding of how to properly use select. Generally, the return values are derived from the contents of the database, but select can also be used to return the value of simple expressions. Select is a read-only command and will not modify the database unless a select is embedded in a different command, such as insert into select. SQL tables. The main SQL data structure is the table. Tables are used for both storage and for data manipulation. We have seen how to define tables with the create table command, but let's look at some of the details. A table consists of a heading and a body. The heading defines the name and type, in SQLite the affinity of each column. Column names must be unique within the table. The heading also defines the order of the columns, which is fixed as part of the table definition. The table body contains all of the rows. Each row consists of one data element for each column. All of the rows in a table must have the same number of data elements, one for each column. Each element can hold exactly one data value or a null. SQL tables are allowed to hold duplicate rows. Tables can contain multiple rows where every user-defined column has an equivalent corresponding value. Duplicate rows are normally undesirable in practice, but they are allowed. The rows in a SQL table are unordered. When a table is displayed or written down, it will have some inherent ordering, but conceptually tables have no ordering. The order of insertion has no meaning to the database. The rows of an SQL table have no defined order. A very common mistake is to assume a given query will always return rows in the same order unless you have specifically asked a query to sort the return rows in a specified order. There is no guarantee the rows will continue to come back in the same order. Don't let your application code become dependent on the natural ordering of an unordered query. A different version of SQLite may optimize the query differently, resulting in a different row ordering. Even something as simple as adding or dropping an index can alter the row ordering of an unsorted result. To verify your code is making no assumptions about row order, you can return on Pragma Reserve unordered selects. This will cause SQLite to reverse the natural row ordering of any select statement that does not have any explicit order. Order by clause. See reverse unordered selects in Appendix F for more details. The select pipeline. The select syntax tries to represent a generic framework that is capable of expressing many different types of queries. To achieve this, select has a large number of optional clauses, each with its own set of options and formats. The most general format of a standalone SQLite select statement looks like this. Select distinct, select heading from source tables, where filter expressions, group by grouping expressions, having filter expression, order by ordering expressions, limit count, offset count. Every select command must have a select heading, which defines the return values. Each additional line from where group by represents an optional clause. Each clause represents a step in the select pipeline. Conceptually, the select result of a select statement is calculated by generating a working table and then passing the table through the pipeline. Each step takes the working table as input and performs a specific operation or manipulation and passes the modified table on to the next step. Manipulations operate the whole working table similar to vector or matrix operations. Practically, the database engine takes a few shortcuts and makes plenty of optimizations when processing a query, but the end result should always match what you would get from independently going through each step one at a time. The clauses in a select statement are not evaluated in the same order they are written. Rather, their evaluation order looks something like this. From source tables designates one or more source tables and combines them together into one large working table, where filter expression filters specific rows out of the working table. Group by grouping expressions groups set of rows in the working table based off similar values. Select heading defines the result set columns and if applicable grouping aggregates. Having filter expression filters specific rows out of the group table requires a group by. Distinct eliminates duplicate rows. Order by sorts the rows of the result set. Offset skips over rows at the beginning of the result set, requires a limit, and limit count limits the result count outputs to a specific number of rows. No matter how large or complex a select statement may be, they all follow this basic pattern. To understand how any query works, break it down and look at each individual step. Make sure you understand what the working table looks like before each step, and how that step manipulates and modifies the table, and what the working table looks like when it's passed on to the next step. From clause. The from clause takes one or more source tables from the database and combines them into one large table. Source tables are usually named tables from the database, but they can also be views or subqueries. Subqueries on page 76 for more details for subqueries. Tables are combined using the join operator. Each join combines two tables into a larger table. Three or more tables can be joined together by stringing a series of join operators together. Join operators are evaluated left to right, but there are several different types of joins. Not all of them are commutative or associative. This makes the ordering and grouping very important. If necessary, parentheses can be used to group the joins correctly. Joins are the most important and most powerful database operator. Joins are the only way to bring together information stored in different tables. As we will see in the next chapter, nearly all of database design theory assumes the user is comfortable with joins. If you can master joins, you will well be on your way to mastering relational databases. SQL defines three major types of joins: the cross join, the inner join, and the outer join. Cross join. A cross join matches every row of the first table with every row of the second table. If the input tables have x and y columns respectively, the resulting table will have x plus y columns. If the input table have n and o m rows respectively, the resulting table will have n into m rows. In mathematics, cross join is known as a Cartesian product. The syntax for a cross join is quite simple. Select something from T1 cross join T2. Figure 5.1 shows how a cross join is calculated. Because cross join have the potential to generate extremely large tables, care must be taken only to use them when appropriate. Inner join. Inner join is very similar to a cross join, but it has a built-in condition that is used to limit the number of rows in the resulting table. The conditional is normally used to pair up or match rows from the two source tables. An inner join without any type of conditional expression, or one that always evaluates to true, will result in a cross join. If the input tables have x and y columns respectively, the resulting table will have no more than x plus y columns. In some cases, it can have fewer. If the input tables have n and m rows respectively, the resulting table can have anywhere from 0 to n m rows. Depending on the condition, an inner join is the most common type of join and is the result of join that makes the inner keyword optional. There are three primary ways to specify the conditional. The first with an on expression. This provides a simple expression that is evaluated for each potential row. Only those rows that evaluate to true are actually joined. A join on looks like this. Select something from T1, join T2 on conditional expression. An example of this is shown in figure 5.2. If the input tables, so here we are joining based on if A is equal to C. So we are taking each of the row in T1 and each of the row in T2 and then comparing where the A and C are equal and then just outputting them in the final output. If the input tables have C and D columns respectively, the join on will always result in C plus D columns. The conditional expression can be used to test for anything, but the most common type of expression tests for equality between similar columns in both tables. For example, in a business employee database, there is likely to be an employee table that contains, among other things, a name column, an EID column. Any other table that needs to associate rows to a specific employee will also have an EID column that acts as a point of reference to the correct employee. This relationship makes it very common to have queries with on expressions similar to select something from employee, join resource on employee EID is equal to resource EID. This query will result in an output table where the rows from the resource table are correctly matched to their corresponding rows in the employee table. The join has two issues. First, that on condition is a lot of type out for something so common. Second, the resulting table will have two EID columns, but for any given row, the values of those two columns will always be identical. To avoid redundancy and keep the phrasing shorter, inner join conditions can be declared with the using expressions. This expression specifies a list of one or more columns. Select something from T1, join T2 using column 1. Queries from the employee database would now look something like this. Select something from employee, join resource using EID. To appear in a using condition, the column name must exist in both data tables. For each listed column name, the using condition will test for equality between the pairs of columns. The resulting table will have only one instance of each listed column. If this wasn't concise enough, SQL provides an additional shortcut. A natural join is similar to a join using only it automatically tests for equality between the values of every column that exists in both tables. Select something from T1 natural join T2. If the input tables have X and Y columns respectively, a join using or a natural join will result in anywhere from max XY to X plus Y columns. Assuming EID is the only column identifier to appear in both the employee and resource table, our business query becomes extremely simple. Select something from employee, natural join, resource. Natural joins are convenient as they are very concise and allow changes to the key structure of various tables without having to update all of the corresponding queries. They can also be a tad dangerous unless you follow some discipline in naming your columns. Because none of the columns are explicitly named, there is no error checking in the sanity of the join. For example, if no matching columns are found, the join will automatically and without warning degrade to a cross join, just like any other inner join. Similarly, if two columns accidentally end up with the same name, a natural join would automatically include them in the join condition, if you wanted it or not. Outer join. The outer join is an extension of the inner join. The SQL standard defines three types of outer joins: left, right, and full. Currently, the SQLite only supports the left outer join. Outer joins have a conditional that is identical to inner joins expressed using an on using a natural keyword. The initial results is calculated the same way. Once the primary join is calculated, the outer join will take any unjoined rows from one or both tables, pad them out with nulls, and append them to the resulting table. In the case of a left outer join that is done with any unmatched rows from the first table, the table that appears to the left of the word join, Figure 5.3 shows an example of a left outer join. An outer join is just like an inner join, only unmatched rows are included in the results table. This shows the left outer join where unmatched rows from the left T1 table are added to the results. The result of a left outer join will contain at least one instance of every row from the left-hand table. If the input tables have X and Y columns respectively, the resulting table will have no more than X plus Y columns. The exact same number depends on which conditional is used. If the input tables have N and M rows respectively, The resulting table can have anywhere from n to n.m rows. Because they include unmatched rows, outer joins are often specifically used to search for unresolved or dangling rows. Table aliases, because the join operator combines the columns of different tables into one larger table. There may be cases when the resulting working table has multiple columns with the same name. To avoid ambiguity, any part of the select statement can qualify any column reference with the source table name. However, there are some cases when this is still not enough. For example, there are some situations when you need to join a table to itself, resulting in the working table having two instances of the same source table. Not only does this make every column name ambiguous, it makes it impossible to distinguish them using the source table name. Another problem is with the subqueries, as they don't have concrete source table names. To avoid ambiguity within the select statement, any instance of a source table, view, or subquery can be assigned an alias. This is done such as with the as keyword. For example, in the case of a self join, we can assign a unique alias for each of instance of the same table. Select from x as x1, join x as x2 on x1.column1 equal to x2.column2. Or in the case of a subquery, select something from select as sub. Technically, the as keyword is optional, and each source table name can simply be followed with an alias name. This can be quite confusing, however, so it is recommended you use the as keyword. If any of the subquery columns conflict with a column from a standard source table, you can now use the subqualifier as a table name. For example, sub.column1. Once the table alias has been assigned, the original source table name becomes invalid and cannot be used as a column qualifier. You must use the alias instead. Where clause. The where clause is used to filter rows from the working table generated by the from clause. It is very similar to the where clause found in the update and delete commands. An expression is provided that is evaluated for each row. Any row that causes the expression to evaluate to false or null is discarded. The resulting table will have the same number of columns as the original table, but may have fewer rows. It is not considered an error if the where clause eliminates every row in the working table. Figure 5.4 shows how the where clause works. The where clause filters rows based off filter expressions. Some where clauses can get quite complex, resulting in a long series of AND operators used to join sub-expressions together. Most filter for a specific row, however, searching for a specific key clause. Group by clause. The group by clause is used to collapse or flatten groups of rows. Groups can be counted, averaged, or otherwise averaged together. If you need to perform any kind of inter-row operation that requires data from more than one row, chances are you'll need a group by. The group by clause provides a list of grouping expressions and optional collations. Very often, the expressions are simple column references, but they can be arbitrary expressions. The syntax looks something like this: group by, grouping expression, collate, condition name, collation name. The grouping process has two steps. First, the group by expression list is used to arrange the table rows into different groups. Once the groups are defined, the select header, discussed in the next section, defines how these groups are flattened down into a single row. The resulting table will have one row for each group. To split up the working table into groups, the list of expressions is evaluated across each row of the table. All of the rows that produce equivalent values are grouped together. An optional collation can be given with each expression. If the grouping expression involves text values, the collation is used to determine which values are equivalent. For more information on collations, see order by clause on page 74. Figure 5.5 shows how the rows are grouped together with a group by clause. The group by clause groups rows based on a list of grouping expressions. Once grouped together, each collation of rows is collapsed into a single row. This is typically done using aggregate functions that are defined in the select heading, which is described in the next section on page 70. Because it is common to group by using expressions that are defined in the select header, it is possible to simply reference select heading expressions in the group by expression list. If a group by expression is given as a literal integer, that number is used as a column index in the result table defined by the select header. The indexes start at 1 with the leftmost column. A group by expression can also reference a result column alias. Result column aliases are explained in the next section. Select header. The select header is used to define the format and content of the final result table. Any column you want to appear in the final results table must be defined by an expression in the select header. The select heading is the only required step in the select command pipeline. The format of the header is fairly simple, consists of a list of expressions. Every expression is evaluated in the context of each row, producing the final results table. Very often the expressions are simple column references, but they can be any arbitrary expressions involving column references, literal values, or SQL functions. To generate the final query result, the list of expressions is evaluated once each row of the working table. Additionally, you can provide a column name using the as keyword. Select expression as column name. Don't confuse the as keyword used in the select header with one used in the from clause. The select header uses the as keyword to assign a column name to one of the output columns, while the from clauses use the as keyword to assign a source table alias. Providing the output column name is optional but recommended. The column name assigned to a results table is not strictly defined unless the user provides an as column alias. If your application searches for a specific column name in the query results, be sure to assign a known name using as. Assigning a column name will also allow other parts of the select statement to reference an output column by name. Steps in the select pipeline that are processed before the select header, such as the where and group by clause, can also reference output columns by name, just as long as the column expression does not contain an aggregate function. If there is no working table, no from clause, the expression list is evaluated a single time, producing a single row. This row is then used as the working table. This is useful to test and evaluate standalone expressions. Although the select header appears to filter columns from the working table, much like the where clause filters rows, this isn't exactly correct. All of the columns from the original working table are still available to clauses that are processed after the select header. For example, it is possible to sort the results via order by, which is processed after the select header, using a column that doesn't appear in the query output. It would be more accurate to say that the select header tags specific columns for output, not until the whole select pipeline has been processed and the results are ready to be returned. The unused columns stripped out. Figure 5c illustrates this point. The select heading tags specific columns for output. The unused columns are not removed until the query result is actually returned. Later, select clauses such as order by still have access to columns that are not part of the query result. In addition to the standard expressions, select supports two wildcards. A simple asterisk will cause every user-defined column from every source table in the from clause to be output. You can target a specific table or table alias using the format table name.star. Although both of these wildcards are capable of returning more than one column, they can be mixed along with the other expressions in the expression lists. Wildcards cannot use a column alias since they often return more than one column. Be aware that select wildcards will not return an automatically generated row ID columns. To return both the row ID and the user defined columns, simply ask for them. Select row ID, comma star from the table. Wildcards to include any user-defined integer primary key column that have replaced the standard row ID columns. See primary keys on page 40 for more information about how row ID and integer primary key columns interact. In addition to determining the columns of the query result, the select header determines how row groups produced by the group by clause are flattened into a single row. This is done using aggregate functions. An aggregate function takes a column expression as input and aggregates or combines all of the column values from the rows as a group and produces a single output value. Common aggregate functions include count, min, max, and average. Appendix E provides a full list of built-in aggregate functions. Any column or expression that is not passed through an aggregate function will assume whatever value was contained in the last row of the group. However, because SQL tables are unordered and because SQL select header is processed before the order by clause, we don't really know which row is the last. This means the values for any unaggregated output will be taken from some essentially random row in the group. Figure 5.7 shows how this works. The select header will select A, average B, comma C from group by A. The select header will flatten any row groups created by group by. This figure shows how different columns from one row group are flattened into an output row. Any value not computed by an aggregate function comes from the last row. Because A was used as a group by expression, all the rows are known to have the same value. It is safe to return. Column B is run through an aggregate function and is also safe to return. Column C is not safe to return as the order of the rows within a group is undefined. In some cases, picking the value from a random row is not a bad thing. For example, if a select header expression is also used as a group by expression, then we know that column has an equivalent value in every row of a group. No matter which row you choose, you will always get the same value. Where you can run into trouble is when the select header uses column references that were not part of the group by clause, nor were they passed through aggregate functions. In those cases, there is no deterministic way to figure out what the output value will be. To avoid this, when using a group by clause, select header expressions should only use the column references as aggregate function inputs, or the header expressions should match those used in the group by clause. Here are some examples. In this case, all of the expressions are bare column references. To help make things clear, select column 1, sum of column 2 from table 1, group by column 1. That is well formed. This is a well formed statement. The group by clause shows that the rows are being grouped based off the values in column 1 and makes it safe for column 1 to appear in the select header, since every row in a particular group will have an equivalent value in column 1. The select header also references to column 2, but it is fed into an aggregate function. The aggregate function will take all of the column 2 values from different rows in the group and produce a logical answer. In this case, a numerical summation. The result of this statement will be two columns. The first column will have one row for each unique value of the column 1. Each row of the second column will have the sum of all the values in column 2 that are associated with the column 1 value listed in the first result column. More detailed examples can be found at the end of the chapter. The next statement is not well formed. Select column 1, column 2 from table group by column 1. As before, the rows are grouped based off the value in column 1, which makes it safer for column 1 to appear in the select header. The column 2 appears bare, however, and not as an aggregate parameter. When this statement is run, the second return column will contain random values from the original column 2 column. Although every row with a group should have equivalent value in a column or expression that was used as a grouping key, that doesn't always mean the values are the exact same. If a collation such as no case was used, different values such as ABC and small abc are considered equivalent. In these cases, there is no way to know the specific value that will be returned from a select header. For example, create table, table T, insert into table values ABC, insert into table values small abc, select small t from table group by T, collate no case. This query will only return one row, but there is no way to know which specific value will be returned. Finally, the select header contains an aggregate function, but the select statement has no group by clause. The entire working table is treated as a single group. Since flattened groups always return one row, this will cause the query to return only one row, even if the working table contained no rows. Having clause. Functionally, the having clause is identical to the where clause. The having clause consists of a filter expressions that is evaluated for each row of the working table. Any row that evaluates to false or null is filtered out and removed. The resulting table will have the same number of columns but may have fewer rows. The main difference between the where clause and the having clause is where they appear in the select pipeline. The having clause is processed after the group by and select clauses, and having to filter rows based off the results of any group by aggregation. Having clauses can even have their own aggregates, allowing them to filter an aggregate result that are not part of the select header. So I'll read till today, till this part for today.